Welcome to the lecture on compound inequalities. Compound inequalities are two inequalities joined by the words and or. The and case is otherwise known as an intersection, and to find an intersection you're going to be looking for all the values that are common to both sets. The notation for this, if you use words, would be A and B, or if you use symbols, this would be A intersect B, and the symbol for intersection is an upside down U shape. The other kind of problem that we're going to look at today is a union, which is synonymous with the word or, and that means the set of all values in both sets together. So you would see this written as A or B, or the set notation would be A union B, where union is denoted by this U shape. So the first kind of example you're going to see is just two inequalities separated by either the word and or the word or. The first thing you want to do is make sure that the inequalities in the problem are simplified and solved for x. Both of these are. And then you're going to graph each of these inequalities on their own number line. So I'm going to do the first one here, x less than or equal to 7. And then below it, lined up below it, I'm going to do the inequality x less than 2. So the first one, x less than or equal to 7, would have 7. We want a closed circle because of that equal bar, and less than or equal to would be shading to the left. Below that, I want to graph x less than 2. Now when I place this 2, make sure that it's in order compared to the one above. That's kind of why I put 7 off to the right a little bit, so that I could put the 2 a little bit to the left of that, so that they're in numerical order. X less than 2, this one has an open circle around the 2, and less than would be shading to the left. Now for the intersection, which is what this word and means, we're going to draw a third inequality, and if you like, I kind of like to draw these vertical lines that separate the region into 3 separate parts, to the left of 2, between 2 and 7, and to the right of 7, and decide which of these 3 regions is in my intersection, this and. And remember, intersection means where both of them have something in common. So if you look to the left, both of these are shaded in at the same time, so that's going to be in my intersection. So I'm going to shade that in my answer solution. If you look in the middle region, they're not both shaded in, and to the right of 7, they're not both shaded in, so neither of those are going to be in my intersection. Now what about the point 2 itself? Is 2 in both of these solutions? In this case, no, because 2 was not included because of that open circle in this second inequality. So that means it should not be included in the intersection either. So here's the graphical solution. However, when you write your final answer, your instructor is probably going to want you to write this in interval notation. So thinking left to right, on the left here, this is sort of starting out at a minus infinity, and it goes up until 2. Because the 2 has an open circle, we're going to use a parentheses, and the convention is around infinity or minus infinity, you always use parentheses as well. So our final solution for the intersection is minus infinity up to 2. In the second example, now we see the word or. So or here means union. We're going to do the same kind of setup that we did before. We're going to set up 2 separate inequalities lined up underneath each other. So when I see x greater than 3, I'm going to want to plot 3 a little bit to the right, open circle around that 3, and greater than would be shading to the right. X greater than -1, I'm going to put an open circle around the -1, and greater than is also shading to the right. For my solution, I'm going to create a third number line underneath. If you want, you can sort of divide up these regions, and this time for a union, what we want to shade down below here is the 2 sets combined together. So when you look at this, any place you see any shading at all, you should shade that in your solution. So if I look to the left here, there's no shading, so there's no shading in my solution. In the middle, there is some shading. Even though it's not for both, there is some shading involved. So it's going to be shaded in my solution as well. And then after the 3, there's shading also. So here's what my solution would look like. What about the endpoint at -1? It wasn't included in this bottom inequality, and it's not included in the top inequality, so it's going to stay open. In other words, when you look at these two inequalities and you want the union of them, it's like superimposing these two solutions on top of each other. And this top inequality for all these x's greater than 3, they're already included in this bottom graph, so nothing new gets added by combining those two together. Final inequality, here's the graph. What is that as an interval? That would start at -1 and it continues up until infinity. Parentheses around the infinity, parentheses around the -1 because of the open circle. The next couple of examples are the same kinds of problems. However, you have to do a little bit of simplifying first before you can graph. In other words, x plus 4 greater than 0, that's not solved for x yet. So the first thing we're going to need to do is subtract 4, and then we get x is greater than -4. For the second inequality, this isn't solved for x either. This time I'd want to divide both sides by 4 to get rid of that coefficient. And when I divide 0 by a positive 4, it stays 0. And remember here, you do not need to flip the inequality because we were dividing by a positive. So our two inequalities are x greater than -4 and x greater than 0. So let's graph those on two separate inequalities lined up underneath each other. So x greater than -4, open circle, and greater than would be shading to the right. X greater than 0, open circle around the 0, shading to the right. Solution is going to be drawn below it. I'm going to divide this up into my 3 regions. And remember, this is an intersection because of that word and. So here we're looking for where the two graphs overlap. What do they have in common? There's no overlap here. In the middle, both of these are not shaded in, so that's not in the intersection. But here, both of these are shaded in. So our intersection is going to be everything greater than 0. What about 0 itself? It should remain open because it was open in this second inequality. So it's not shaded in for both solutions, so it's not in the intersection. What is this as an interval? This would start at 0 and go up to infinity, open parentheses around both. Okay, in the next example, same idea. First, we need to simplify our inequalities. So for this first one, we subtract 1, and 3 minus 1 becomes 2. And here we subtract 4. 2 minus 4 is -2. No flipping of your inequalities here because you only flip if you multiply or divide by a negative, not add or subtract. So we have x greater than 2, and we have x less than -2. And I'm going to draw each of those. X greater than 2 is an open circle, greater than shades to the right. X less than -2 is another open circle, shading to the left. Final graph underneath. If you divide this up into 3 regions, this time we want an OR, which means union. So we're going to superimpose these two graphs together. So if I see any shading, I'm going to include that shading in my answer. So in this region over here, I do have shading down below, so there should be shading on my solution. There's no shading at all in the middle, and there is shading after 2. Since both of these endpoints are open, they're going to remain open in my union. So when I superimpose the two graphs together, I just get these two tail pieces. Now how do I write this using intervals? I have to do it with 2 intervals, one for each tail piece. So the tail piece on the left starts at -infinity and goes up to -2, parentheses around both. For the second tail piece, this starts at 2 and it goes to infinity, parentheses around both. And if I want my solution to include both of these, we're going to use that set notation for union, which is that U shape. So your final intervals are going to be minus infinity to negative 2, union 2 to infinity. Alright, let's look at the next examples. Here again we want to solve for x first. So on this one I need to divide both sides by a positive 2, which is going to stay x less than 3. For the second inequality, you could do this in two ways. You could distribute that 3 across first and then solve from there. Or, because 3 divides so nice and evenly into 6, you might want to just go ahead and divide by 3 right away. That's going to give you x minus 2 is greater than 6 divided by 3 is also 2. Now when I add 2 to both sides, we get x greater than 4. Now this is an intersection, and what we want to find the intersection between is this x less than 3, the one on the left, and then also an x greater than 4, the one on the right. So let's graph each of those. Here's 3, open circle, less than, shades to the left. Here's 4, open circle, greater than, shades to the right. Here's my final solution. If I divide this into my 3 regions, where do they overlap? Over here on the left they do not. In the middle there's no shading at all. And on the right they're not both shaded in. So they don't have anything in common. So in this example the intersection is actually nothing. There is no intersection at all. You would have just an empty number line for your graph. How do we write this for a final solution? You could just write the empty set. There's no interval that describes this because there weren't any values that worked. So our final answer is no solution, no intersection. For this example here, we want to simplify for x. So the first thing I would do here is add 6 to both sides to get that x term by itself. So that gives us 2x is less than or equal to negative 12. And then I would want to divide both sides by 2, and that's going to give me x is less than or equal to negative 6. I was dividing by a positive, so I don't have to flip the inequality. For the second inequality, divide both sides by 2. Again, we're dividing by a positive, so you don't have to flip. And this is going to give me x greater than or equal to negative 9. And this word in between was an or, so that's going to be a union problem. So we want x less than or equal to negative 6 and x greater than or equal to negative 9. So let's graph each of those. Now negative 6 and negative 9, which one is further to the left on a number line? Negative 9 is. So we want to make sure you put negative 9 to the left and negative 6 to the right. So we want x less than or equal to negative 6. So that's a closed circle this time because of that equal bar. And less than goes to the left. X greater than or equal to negative 9 is another closed circle, greater than shades to the right. For our final solution, dividing this up into our 3 regions, remember that this was a union, so we're looking for the for all the places where this has been shaded in. We want to superimpose the 2 graphs together. So if I see any shading at all, I'm going to shade in on my solution number line as well. So in this third region, or this leftmost region, there is some shading, so I want to shade on my solution. In the middle there was shading, so I want to shade on my solution. And on the right there's shading as well. In other words, when you superimpose these 2 graphs together, they cover the entire number line. So this is your solution. It's actually everything. How do you write that as an interval? Since everything works as an interval, that would be minus infinity up to positive infinity. All real numbers. Okay, let's see a couple more examples like this. This next one is a little bit different. This is a triple inequality. So just to review that a little bit, we have a triple inequality, which is really 2 inequalities nested together. This is really 2 problems. We have this on the left needs to be true at the same time as this inequality on the right. This is an implied intersection problem. The long way to think about this is it really means negative 1 needs to be less than 2x minus 5 all over 6, and at the same time 2x minus 5 over 6 needs to be less than or equal to 6. Now you could solve each of these individually and then do our number lines just like we've been doing, but as a shortcut for these triple inequalities, a lot of times what we'll do is we'll solve both of these inequalities simultaneously. So to do that, what you want to try and do is in the middle section right here, you want to try to get as your goal just x by itself. So when I look at what I have initially here, the first thing that sort of bothers me is that fraction with the 6 in the denominator. So what I would choose to do is clear out that denominator right off the bat. And we would do that by undoing this division by 6, which is to multiply by 6. So we're going to multiply the left by 6, this middle part by 6, and the right side by 6. You have to do it 3 times because there's 3 pieces to this triple inequality. So 6 times negative 1 becomes negative 6. The 6 that we multiply in the middle serves the purpose of canceling out the 6 in the denominator. The only thing you should have left in the middle is that numerator. Don't be tempted to try and multiply the middle or the numerator by 6 as well. A lot of students will write 12x minus 30 in the middle here, and that would be incorrect. You'd be multiplying by too many 6's. So this 6 only cancels out that 6, and that's it. On the right hand side, 6 times 6 is 36. So here's our new simplified triple inequality with no more fraction in the denominator. Now we're still trying to get x by itself in the middle. So now what I'd want to get rid of is this negative 5, and to undo that, we could add 5 in the middle, on the left, and on the right. Negative 6 plus 5 is negative 1. In the middle we have 2x, and 36 plus 5 is 41. And to finish off the problem and get x all by itself, we want to get rid of that coefficient, which right now is being multiplied. So to undo that multiplication, we would divide by 2. We're dividing by a positive, so we don't have to do any flipping. And this is going to give me negative 1/2 less than x less than or equal to 41/2. Now graphically, what does that mean? On a number line, when you have a triple inequality like that, what it means is you want all the x's in between negative 1/2 and 41/2. We want all the x's greater than negative 1/2, but at the same time less than or equal to 41/2. So that's going to be all these x's in the middle. Then if you look at the endpoints, there's no equal bar on this left-hand side, so the negative 1/2 should be open. But there is an equal bar on the right-hand endpoint, so the right-hand endpoint at 41/2 is closed. For your final interval solution, if you want to write this using interval notation, this starts at negative 1/2 and it goes up to 41/2. Open parentheses around the negative 1/2 because of the open circle, bracket around the 41/2 because of the closed circle. And here's our final solution. Typically, triple inequalities will always give you an interval that starts and stops at specific endpoints. It gives you this sort of middle interval in between. Okay, let's try one more example here. With a union, we have 3x less than x plus 10 or negative x plus 1 greater than 10. So if I try to simplify these first, remember you want to get x by itself. So I'm going to subtract this x over to the left side. That gives me 2x less than 10. And if I divide both sides by 2, that leaves me with x less than 5. On the right-hand side here, we'd want to get the numbers together, so I could subtract 1. That's going to give me negative x greater than 9. And I still have that negative in front of the x, which is like a coefficient of negative 1. So to undo that coefficient, we could divide both sides by -1. And notice here, you're dividing by a negative, so you must flip your inequality. So this greater than switches to a less than -9. This is an or in between, so this is a union. So to figure out our final solution, you need to graph each of these individual inequalities and take their union. So we have x less than 5, open circle around the 5, less than, shades to the left, and then x less than -9, -9 would be over here to the left, open circle, less than, shades to the left. For the final union, if I divide this up and sort of superimpose these two graphs together, anywhere I see shading, I'm going to shade in my solution. So there's shading for both of these. There's shading right here, so that gets included as well. And then there's no more shading after that, so this is going to stop at 5. 5 was not included in my shading because of that open circle, so it's going to stay open down here. In other words, when I superimpose these two graphs together, all this stuff to the left of -9 was already included in the solution x less than 5, so nothing new was added. So here's my final graph. What would that be as an interval? Well, to the left we're starting at -infinity and we're going up to 5, open parentheses, around both. For these next two examples, these are going to be done exactly the same way we've done them. However, what you're starting with isn't necessarily written as an inequality, it's written as an interval. So you're going to graph each of these intervals on a number line and then find either their union or their intersection, depending on what symbol you see. So first I'm going to take this interval -2 to 3 and I'm going to graph it on a number line. This says start at -2 and go up to 3. So we're going to shade in all those numbers in between. And notice I used parentheses around each endpoint, so these should be open circles. For the second inequality, I have -infinity up to -3. And be careful here with your order. -3 is slightly to the left of -2, so -3 is going to be right about there. And this interval, -infinity to -3, means start at -infinity, which would be way over here to the left, and go up until you hit -3. And these were both open circles because of those parentheses. So if this is these are my two intervals, underneath for my solution, we want whatever this symbol represents, and this is that upside down U shape, which means intersection. So I want the intersection of these regions. So where do these two regions overlap? Where are they both shaded in at the same time? Well, they're not both shaded in here, they're not shaded in here, they're not both shaded in here, they're not both shaded in here. So again, I have that empty number line. There's no overlap at all. So my final solution is actually nothing. I have the empty set for my solution. Okay? So there was no intersection in this example. Let's try another one. This time I'm going to graph the interval -1, 2. So we're going to start at -1 and we're going to go up to 2, everything in between. And these were brackets, so those correspond to closed circles. And then we have the interval 0 to 5. Make sure you're placing these in order. 0 would be a little bit to the right of -1, so maybe about there. And 5 would be to the right of that 2, so maybe over here. And these are both open parentheses, so we want open circles. And 0 to 5 would be everything in between. So for our final solution, we want this, and that means union, U for union. So anywhere that I see shading, I want to shade in my answer. So let me draw in all my lines through all these key points. I see shading between -1 and 0 right here. I see shading between 0 and 2, and I see shading between 2 and 5, and that's it. Nothing to the right of 5, nothing to the left of -1. How about some endpoints here? Well, -1 was shaded in up above because of that closed circle, so it's going to be shaded in my union. 0 was shaded in up here, even though it was open down here, so it does get colored in. 2 was colored in up here, so it's included down here. And 5 was not shaded in down here or up here, so it remains open in the union. So my final graph looks like this. What is that as an interval? You start at -1, and you go up to 5, open parentheses around the 5, bracket around the -1. So imagine superimposing these two graphs together. What it leaves you with is your lowest endpoint on the left up to your highest endpoint on the right. For our last example, we're going to do one more of these triple inequalities. But this time, this triple inequality is a sort of a special case because this one has variables on the left, variables in the middle, and variables on the right. So when you have variables in all three positions, you have to be a little bit more careful. So this is a special case, and we're going to have to solve it with a little bit more work. So when you have variables in all three positions, you must split this up into two separate problems. If you recall our earlier triple inequality, and let me back up to remind you, in this example up here, we were able to do the same work simultaneously to solve this inequality. What makes this example different from the one we're about to do is the x's in this example only occurred in the middle. There were no x's on the left, no x's on the right. So this is the easy case. If you only have x's in the middle, then you can perform your algebra to get that x isolated in the middle, just like we did on this problem. Unfortunately, in this last example, we can't do that because we don't just have x in the middle, we have x in all three places. So what we're going to have to do is look at this problem on the left separately from this problem on the right. We're going to have to solve each of these independently from each other. Now this is a triple inequality, which means the problem on the left needs to be true at the same time as the problem on the right. So anytime you have a triple inequality, that's always an implied intersection, or in this case the word and. We need this to be true and this to be true at the same time. So once we solve each of these two inequalities, we're going to need to make sure that we take the intersection of those two solutions. So let's start with this first one here. If I want to solve this for x, we would want to subtract x probably to the right side, get those x's together. That would give me 3 less than x plus 1. And then if I isolate that x by subtracting 1, I'm going to get 2 less than x. Now I want you to be careful here because this is backwards from how we like to see it in mathematics. In math, we tend to like having the variable on the left-hand side and the number on the right-hand side. If you don't swap it around, you're most likely going to be shading this in the wrong direction. A lot of times when students see this, they see that less than symbol, and so they automatically shade to the left of 2. But if you read this carefully, this really means, if we switch it around, x on the left, 2 on the right, flip that inequality back around to match it, and that means we really want all the x's greater than 2. So that's going to have as its solution on a number line, open circle, shading to the right. So don't shade to the left, even though you see a less than symbol up here. When you flip it around, it's really supposed to be x is greater than 2, shading to the right. So that's the solution to the left problem. Now we need to do the right problem. So if we go and solve this, we'd want to subtract 2x from both sides to get those x's together. We get 1 is less than 2x plus 6. Subtract 6. We get negative 5 is less than 2x. And then finish it off by dividing by a positive 2. You don't need to flip because we're dividing by a positive, but you might want to flip now because, again, it's backwards. The x is on the wrong side. So if I flip this around, that less than changes back into a greater than. So if we graph that below this other one, we want all the x's greater than negative 5 halves. Negative 5 halves would be a little bit to the left here, open circle, and greater than means shading to the right. Now when I go to finish off the problem, and this is key, a lot of students can do this problem just fine, solving each of these two separate problems, but then the key thing that they forget to do is to take the intersection of these two solutions. So in your final answer, you need to draw a third number line, and you need to divide this up and look to see where is that intersection. Where are these two graphs shaded in both at the same time? And here is where they're both shaded in at the same time. That's what they have in common. So my final answer is only going to be the x's greater than 2. And since 2 was open up here, it's going to remain open in my intersection. So the only x's that work for both of these two separate problems are the x's greater than 2. As an interval, that's starting at 2 and going up to infinity. Open parentheses around that 2. So be careful. If you see a triple inequality where there's variables in all three positions, in the left, on the right, and in the middle, you need to split it up into two separate inequalities, simplify and solve each one, and then take the intersection of those two solutions. If you only have x in the middle of the triple inequality and not on the left or the right, then you can solve the inequality simultaneously without having to split it up into two problems. So just be careful. Alright, that concludes our lecture on compound inequalities. Good luck.